All right, hello geometry. This is how we're going to be doing notes right now. So we're going to be taking the 12-1 notes. On HeadRush, I do have the copy of the one that I'm writing on right now, also a blank version, so you can kind of fill it in as we go. So here we go, 12-1. We are skipping to chapter 12 because hopefully by the time you can all come back, we will be doing the chapter 10 and 11 project. So hopefully we'll do that, otherwise we'll just do it online. Okay, so today we're going to do lines that intersect circles. So if you remember back to our magic circle, something called a chord came up. We're also going to be talking about secants and tangents, and also properties of these to solve problems. So that is what we're doing today in 12-1. All right, so the first piece here is the definitions of what we're looking at. And again, you probably defined a few of these in the circle project. But a chord is a segment, so be careful that you know that it's a segment because later on we'll be talking about lines. So segment, remember, has a start and an end. So here we are with our label of a chord, starts there, ends there, and it's on the circumference of the circle. So that's our chord. Endpoints lie on a circle. All right, and so again, technically that's a circumference. All right, then the next one is a secant, and again, I mentioned that there were going to be lines. Secants are basically chords that we've made into lines, okay? So they intersect a circle at 2 points, and those 2 points are on the circumference, but then it goes through. Okay, so here we are with secant line L, because of course we love to use cursive L's for lines. So again, I could have made this one into a secant as well by extending it out, and now I have a chord AB if I name it as just AB with a segment on top. But if I wanted to name it as a secant, then I would have done AB with the line above it. So it kind of just depends, and again, of course, this is the actual secant that they had. All right. Then we have tangent, and a tangent is also a line, and it's a line that intersects exactly 1 point of the circle. So this is where we have to get kind of creative. A lot of times I end up making my dots where they intersect very large, just to make up for error. But the idea is that this line goes along its way and then all of a sudden just touches this circle at exactly this 1 point. It's called the point of tangency, okay? And so in this case, C is the point of tangency. And of course, we can make a line M in this case, or whatever letters could be on it. But the idea is that the tangent is a line that intersects the circle at exactly 1 point, doesn't go through it like chords and secants, and then it kind of just bounces back off. And it intersects it at this point of tangency. So those are some of the pieces. Again, we sort of saw chord in the project, but here we go. All right, so then we're going to identify a few of these things, knowing that a lot of geometry is this new language. So here we go. So we're going to identify a chord from this image. And remember that from our definition from the previous slide, a chord is a segment whose endpoints lie on the circle. So we can't, for instance, use this letter here, because remember that this kind of fancy M here just means line M, and chords are not lines. So I need something that is on one edge of the circle, on another edge of the circumference of the circle, and stops. So in this case, I've identified that Km could be a chord, and of course chords, well, that's a bad K. Chords are segments, so we just put a segment above it. Other than Km, we also have Jm, that is a straight line. So Jm is also another option. And then of course, MK and MJ backwards if you wanted those as well. All right, then we have secants, and remember that from our definition, secants are basically chords, but they're made into a line. So if we notice, I cannot write Km because Km doesn't have a line extending from it. So in that case, Km is not a chord and a secant, it's just a chord. Jm, however, does have those arrows that go out, so we can write Jm as a secant, and then also with a line drawing above it. So that's your Jm. And then it doesn't look like any of the other lines is your tangent because it doesn't go through the circle. So I need something that's a secant that would go through it. So Moving on to our next one, the tangent, remember, is the line in the same plane as a circle that intersects at exactly 1 point. So we go ahead and identify the tangent, and that's this one. It's technically intersecting at point H. That's what they're saying here. So in that case, our tangent line is line, oops, let's jump into the M. It's line M. All right. And we can't say it's line MH because remember, lowercase letters aren't points, so we can't name it any other way. Then we go back to some definitions that we hopefully know. Diameter is across the circle. It's kind of what they call half of the circle. And then the radii is half of the diameter. And we did do these in the Magic Circle project. But either way, the diameter goes across the circle through the midpoint. So we do have to only use Km because that's the only one that goes through the center of the circle. Jm doesn't. So nope. So that means that our diameter is Km. And our radii, there's actually quite a few of them because it goes from the middle of the circle out. So we could do Lk, Lj, Lm. As long as it has an L in it, it's probably a radii. So Lk is one of our radius, and it's a segment. Lj is one of our radii. It's a segment as well. And Lm. All right. So that was just the terminology that we now know. Chords, secants, tangents, and then diameters and radii. All right, moving on, a few more pieces about circles. So when you have two circles, for instance, that are congruent, if you remember back to our idea of congruent, congruent was same length and same angles, but there really aren't any angles in a circle. So in that case, we're just talking about the same length, and the only length that's in a circle is its radii. So in that case, if you happen to have, for instance, in this case, CA and the diameter or radius here, which is BD, and the fact that they are the same, which is what they've said here, AC and BD are the same, that means that we do have a set of congruent circles. Also, you'll notice here in this definition, they did it backwards and forwards. If circle A and B are equal, then the radius are equal. If the radius are equal, then the circles are equal. And that is how you mention what a circle is. You draw a circle with a dot in it, and then you use its center point. So in this case, center point. So that's why this one's called circle A, because A is in the center, and this is circle B. B is in the center. All right, then we have something called concentric circles. You've probably heard that word before, but concentric in this case, they're coplanar, so on the same sheet of paper in this case. And then circles with the same center. So as long as they both are named circle B or whatever the letter happens to be, the only difference then becomes their radii length. So that's how you would determine if we're talking about little circle B or big circle B. All right, so those are both circle B, and they're concentric because they share a center. All right. Then moving on to coplanar circles, so again on the same sheet of paper here, that intersect at exactly 1 point, and they're called tangent circles because technically they meet at a point of tangency. So they share a point of tangency. And again, if you're not very good at drawing circles and then also circles that meet at exactly 1 point, this could get interesting. But the idea is that this circle here with the larger one around it does in fact meet at just this one little point, and that is your point of tangency. All right, then over here we have externally tangent, so versus internally tangent, and again they just meet at 1 point, and that point is right here, your point of tangency. All righty, so those are a few of our pieces there. So now that we know about points of tangency, we're going to identify tangents of circles and find the length of each radius. And you might think that length might come from distance formula or whatever, but in this case, it is lined up so that they're just on, your radius can be found exactly on the line of the grid. So Again, you could use distance formula eventually, and so if you need that reference, your distance formula is technically the Pythagorean theorem, but you'd take your y's and subtract them and add that to your x's subtracted and squared, and then you'd get the square root. So if for some reason they wanted you to find this radius, you'd need your coordinates of both of those. Alrighty. So the radius of r, they're looking for the length. And so if we go with the nice horizontal line on the grid, we do have two squares, double checking that this is by ones. So these are all 1 unit. That means that this is going to be a length of 2 for radius r. Radius s there, again, we're not going to use this diagonal one because that's not going to be helpful. And in fact, even kind of going across here is not very helpful. So instead we might go up. And if it is halfway across, it's pretty generally exactly looking like halfway. So in this case, this is technically 1.5. And then we have 2 and 2.5 and 3. And so the distance between the 1.5 where the S center is and then the 3 where it goes out means that this is going to be 1.5 units. So radius r, as it has a bigger radius because circle r has a bigger radius than circle S. You can see that. Then we look for our point of tangency. So this is actually looking for a coordinate. We're looking for the coordinate where they meet. So if you refer back to the notes, we're looking for this point of tangency. But of course, on this example, you have kind of this snowman looking thing here. So in that case, we're looking for the coordinates of this point. So double check, especially since it's on an axis, that we're going left or right first. So left 2, which means -2, and then up or down none. So -2, 0 is the point of tangency. Then they want the equation of the tangent line. And so you can go back to your understanding of linear equations. Remember that in a linear equation, you've got your slope here as your m, and your b value is your y-intercept. You could take 2 points and find the slope, but hopefully we know by now that anything that is a horizontal line has just a y equals that number. So we have to check what the y value is, and since it's at 0, that means that the equation of the line is y equals 0. If it was a vertical line, that would be x equals, versus if you actually needed to find this, you would take 2 points and find your slope. Remember that the slope equation is going to take y2 minus y1 over x2 minus x1. And once you have those points, you plug it in for slope. And then you can find your intercept either by looking visually, or you can actually plug in a point and find it algebraically. So if we get to one of those problems, we'll go over that, but we have done that in Algebra 1. Alrighty. So that is lines that intersect circles of tangents. Then we've got a few more images of tangent, or common tangents in this case. So it's a line that is tangent to 2 circles at the same exact time. So again, very hard to draw, so yay for computer generation here. This line here, line L, touches circle B and A at that one tangent point. And then we've got line M, which also touches at these 2 points, and maybe eventually you'll have to find the equation of that line. And they have common external tangent points. Super. Then instead of having the outside points, you could also have internal tangents. So that just means that the lines, if they were to go through, would go between the 2 circles versus on top like the other ones did. So again, these would be all of your common points of tangency there. All right, few pieces. With Unit 12, and we'll see how this goes, but with Unit 12, we do normally get a theorem sheet because there are a lot of theorems to double check that you understand. So the next page here is actually the first page of the theorem sheet. So if we take a look at the theorems that you are supposed to know for this, it turns out that tangents have, other than a special idea of meeting at one point, if you draw the radius from that point of tangency, you actually make something that meets at 90 degrees, which is super helpful because anything that meets at 90 degrees could then lead to right triangles. Could also lead to Pythagorean theorem. We could start to use some trig. There's a lot of ideas that when you get your 90 degrees, we get to use. So this first part is converse to the second part. So all it just means is if there is a line that has this tangent point, then it is perpendicular to the radius drawn from that point. So the way that I said here. So line with a radius, you get to lead to the conclusion is this perpendicular or 90-degree angle. Okay, then of course backwards. If you happen to know that this is right here, this angle right there, then we know that it is in fact a tangent line. So this one's going from the 90 degrees to the fact that it's tangent. And this one's going from tangent to 90 degrees. So again, those are your converse statements. All right, and again, this sheet will be part of my scanned notes, but I will also make a copy available of the theorems sheet in a link on HeadRush as well. So you'll get to see all of them. I have also made up nicknames for these just so that we can kind of reference them a little easier because Theorem 1111 is really not a great name. And so this one in the past, shout out to previous schools, has actually been called the Tp Theorem. So yes, TP like toilet paper, because if you imagine how maybe a roll of toilet paper might be hanging on a toilet paper roll, you've got this toilet paper, not usually up here, of course, that hangs down. And of course, you can go into that argument of does it hang backwards or forwards and all that good stuff. But that is why we call it the TP theorem, which if you have some based on this coronavirus issue, yay for you. So hopefully you've stocked up. So there's the TP theorem. And then this next one I actually like to call the Party Hat theorem. If you could turn sideways with me here for a second, we're imagining that this is a person and they're super happy because they are at a party and they're wearing a hat. Yes? Okay. So that is the idea of the Party Hat theorem. But if we go through what actually is the Party Hat theorem, when they construct party hats, it turns out that they better construct them where they are perfect. Otherwise, you're going to have this issue where your party hat is like going off to the side, which we're not doing. So on that note, that means that this segment and this segment are equal in length. So if we look at each of these, again, the official definition of 1113 theorem, but we're calling it the Party Hat theorem, is if two segments are tangent to a circle from the same external point. So here's your external point. And the fact that they are tangent here and here, then the segments are congruent. So BA in this case and CA have the same length. So that's what's happening here. So if you see a party hat, yay, you have two sides that are the same. Yay for that. All right. Moving on to some examples, because of course we're going to use these. This one here, if you can't reference, is the TP theorem. So again, we're imagining the toilet paper roll, and we've got the toilet paper hanging off here. So that means that we have a right triangle, which of course has already been drawn here. So we don't really need to be too creative about that. So apparently Mount Mitchell. So we're imagining that this is Mount Mitchell. There's some snow on the top and, you know, a little tree going off the side there. Okay, so anyway, this is Mount Mitchell, and its peak up here at E is 6,684 feet above the Earth's surface. So what is the distance from the peak to the horizon? So notice this question mark here, that's what we're trying to find, and we're going to round it to the nearest mile. So here we are with a right triangle. All right, and they've given you some information here. If you didn't know, to the center of the Earth is about 4,000 miles. I'm sure it's got a decimal in it, but we're getting less creative and specific today. So 4,000 miles to the center of the Earth, which means that if we draw this right triangle, maybe helping ourselves out a little bit here, from H to C, we have 4,000. From C to D, we don't know, but we do know that D to E is this 6,684 miles. And so we know that it's 4,000 from C to D, so we do know that length, sorry. And then from D to E, not drawn to scale clearly, is 6,684 feet. Got to watch out because this is miles and this is miles. All right. So we are trying to find this piece here. And so eventually we can just use the Pythagorean theorem, which I mentioned earlier, but we do need to convert everything into the same unit. So it does say to find the answer to the nearest miles. So it might be nice to actually convert 6,684 thousand feet into, anyway, lots of words there, into miles. So if we do that, remember, you can convert depending on what's happening, but proportions are the best. So turns out that there are 5,280 feet in every mile. If you didn't know that, a lot of people say 5 tomatoes because, anyway, that's weird, but it's 5280. One of those things that might be nice to memorize. And so if we're going to convert this into miles, or use this to convert into miles, I need to write feet on the top so that I can find this certain number of miles on the bottom. So that means I'm going to put 6,684 on the top. And then I'm going to use cross multiplication, which is going to result in 6,684, and then divide by 5,280. And so some of you probably already did that knowing it, but it is nice to know why you would have divided versus multiplied by 5,280. So we take that and divide, and apparently we get 1.27. So instead of 6,684 feet, it's 1.27 miles. So in that case, this entire length of the hypotenuse is 4,001.27 miles. So now we have the hypotenuse, we have a leg, we don't have this other leg, and so if we call this the C from the Pythagorean theorem, and this the A and this the B, that means that we're going to take A squared plus B squared, and it should equal C squared, or 4,000 squared plus the value we don't know equals 4,001.27 squared. Doing the math, you make this squared and this squared, and so once you do that, you're going to get the fact that B squared, taking it away, is not the number that I meant. Oh, that's a really big number. Okay. So again, you're going to take the number of 4,001.27 squared, which is huge, and then you're going to subtract 4,000 squared, and that does not mean, please, that it's 1.27 squared, because that is not the same. So what you end up getting is 4,001.27 squared, and then that's this giant number, and then I multiplied, so that is where that is a problem. I'm going to take 1601. It's very hard to type on. 61.61. And we're going to subtract 4,000 squared, thank you, instead of multiply. That's why I got such a big number. All right, so now we get 10,161.61, which we're going to have to square root because we don't want B squared, we want B. So if we take the square root, our B value, or this distance from the top of the mountain to this point on the horizon, is going to be 100.80. It does say to the nearest mile, so 0.8 would mean that this is actually 101 miles. And that is the length of EH, typically. All right. So that's how you would use the TP theorem or toilet paper theorem to find this right triangle and then find out that distance from the top of the mountain to this point on the horizon until you can't see the world anymore, apparently. Very helpful. All right. Yay, Mount Mitchell. All right. Then this last piece here uses the Party Hat Theorem, so hopefully you can see that this is your party hat guy. I know, that's kind of a fun face. Anyway, so the idea is using this theorem that the line or segment here and this segment are going to equal each other. And of course, we don't just put a number on there, we put an expression, because what would be the fun in that? So that means that 3 plus 6x's are going to equal this guy here, 14x minus 8. Because FE, according to the theorem, is equal in length to FG. And technically, we would want to put a little m here. All right, so the measure of that equals the measure of that. In order to solve this, this is where you get your algebra going. So we'd distribute the 2, or divide if you wanted to. Distribute the 2 and get 6 plus 12x equal to 14x minus 8. Move our letters with our letters. And our constants or numbers with our numbers. And we get an x of 7. Cool, that's not the answer because it says find FG, which means that you need to plug this 7 back in and get 14 times 7 minus 8. 14 times 7 is 98, and then you're going to subtract 8 from that, so apparently FG, the measure of it, is 90 units, whatever that happens to be. So FG is 90. Again, don't stop here. It's not quite your answer. Read the problem that says, yes, they're tangent, yay, find FG. Alrighty. So hopefully that was a super duper party because we were wearing party hats. And now you know all about 12.1 and you're totally ready for the assignment. All right. I'm going to do a video about the assignment as well, so you can have steps to walk through them, but really you should do the assignment by yourself. Check them with the answer key that's posted on HeadRush, and then if you need more help, since you can't ask me, technically, you could watch the video of me solving it. Sweet. All right, enjoy. Hopefully you understand 12.1.